What if I told you that we could get to one of the most fundamental results of Einstein's special relativity, but without using any of his postulates? No weird paradoxes, no warping of space or time, just pure classical Newtonian mechanics. Well, get ready, because we're about to uncover a path to relativity that's been hiding in plain sight this whole time.
So here's our game plan. First, we're going to pinpoint a major flaw in classical physics. Then, we'll look at two very different ways to get to relativity, and focus on the one that's way more intuitive. We'll see how a simple idea, that energy has mass, changes absolutely everything. After that, we'll actually solve Newton's own equation to find a shocking result, which will give us the universe's ultimate speed limit. And finally, we'll see how this beautifully ties two huge pillars of physics together.
All right, let's kick things off with a problem. You see, for all its incredible power, Newtonian mechanics has a breaking point, a place where its predictions just completely fall apart when faced with reality.
And that breaking point becomes undeniable when you look inside a particle accelerator. According to Newton, right, if you keep pushing something, it should just keep going faster and faster. But that's not what happens. As these tiny particles get screamingly fast, their inertia, their resistance to being pushed, just skyrockets. It's like they slam into this invisible wall. No matter how much energy you pour in, they can never, ever reach the speed of light. And Newtonian physics has absolutely no explanation for this.
Now, of course, this is all perfectly explained by special relativity. But how we get to that explanation is what's so interesting today. It turns out there's more than one path to this truth, and we're about to take the road less traveled.
And just so you know where this is all coming from, our whole journey today is based on the derivation laid out in Chapter 5 of Newton and Relativity by Sester, Clementi, and Korff. And here's what's so brilliant about their approach. The one key ingredient we need, mass-energy equivalence, was something they already derived back in Chapter 3 of their book using nothing but classical physics. No relativistic postulates. That is a crucial point. We're building on a foundation that is purely classical.
And this chart just lays it all out beautifully. You've got the standard path from Einstein and Lorentz on one side. It starts by assuming the speed of light is constant, which leads to complicated math and really weird paradoxical ideas like length contraction, shrinking rulers. But the alternative path we're taking, it starts with a simple physical principle, mass-energy equivalence. It uses Newton's second law. And get this, it completely avoids all those paradoxes. It's just so much more direct.
So let's really dig into that core concept, because this one simple idea is what unlocks this entire puzzle. It all comes down to the weight, or more accurately, the mass of energy itself.
Here's the big idea in a nutshell. Mass is energy, and energy has mass. It's that simple. So when you add energy to something, any kind of energy, you are also literally adding mass. When you push an object and give it kinetic energy, you are making it physically more massive. The total mass of that moving object is its original mass plus the mass of its motion.
And this is where it gets really cool, because it creates this amazing feedback loop. The faster you make something go, the more kinetic energy it has. That extra energy adds to its total mass. And a more massive object is, by definition, harder to accelerate. So the faster you go, the heavier you get, and the harder it becomes to go even faster. That invisible wall we saw in the particle accelerator? This is it. This is the reason it exists.
Okay, so let's move to the math and see how this all clicks into place. We're about to find a relativistic secret that's been hiding inside one of the most famous classical equations of all time.
Now, this is the full general form of Newton's second law. It says that the energy you put into a system dE gets split between two different jobs. The first part, mv/dv, is the one we all know and love. It makes the object speed up. But look at that second term, v²dm. That's the secret sauce. It says some of the energy goes into making the object heavier, into increasing its mass, dm. Now, at everyday speeds, that second term is so tiny you'd never notice it. But as you get close to the speed of light, it starts to take over.
But here's the catch. You can't solve this equation on its own. It's stuck. This is where our big idea comes to the rescue. We know that any little bit of energy you add, dE, is equivalent to a little bit of mass you add, dm, connected by c². So we can substitute c² dm in for dE. And just like that, the equation is transformed. Now it only has terms for mass and velocity. It's finally solvable.
And when we integrate that now solvable equation, look what just pops out. It's incredible. Straight from Newtonian mechanics, with just that one little insight about the mass of energy, we derive this famous formula.
That thing in the denominator is the Lorentz factor, a cornerstone of special relativity. We got there without a single one of Einstein's postulates.
Okay, now for the payoff. Let's see how this brand new formula we just built directly answers the mystery that we started with, that cosmic speed limit.
If you just look at the formula, the consequence is staring you right in the face. As your velocity, v, gets closer and closer to the speed of light, c, the fraction v squared c squared gets closer and closer to 1. That means the entire denominator gets closer and closer to 0. And what happens when you divide by a number that's almost 0? The result blows up to infinity. Your mass and momentum would become infinite. You'd need infinite energy to get there. It's impossible. And that is why nothing with mass can ever reach the speed of light.
So let's just step back and appreciate what this approach really gives us. This isn't just some neat mathematical trick. It's a deep, profound bridge between two entire worlds of physics.
I mean, think about the journey we just took. We started with Newton's second law, pure classical mechanics. We combined it with one single principle, mass-energy equivalence. And from that simple combination, we derived a fundamental result of special relativity. It shows that relativity isn't some crazy departure from the past. It's a deeper truth that was already sleeping inside of classical physics, just waiting for us to find it.
And you don't have to take my word for it. The authors of the source material sum it up perfectly. They write, "We have entered the field of relativity directly from classical physics without setting up postulates or resorting to the paradoxical premises of Einstein's established interpretation." That's the whole point. It's a completely self-contained logical path.
And that leaves us with a pretty incredible thought to chew on. If a law as fundamental as this was lurking inside equations we've had for centuries, it really makes you wonder, doesn't it? What other amazing secrets about our universe are sitting right there in front of us, just hiding in plain sight?